So, ladies and gentlemen, with the latest iteration of AlphaFold, aka AlphaFold 3, the experts at DeepMind and their partners at Isomorphic Labs have cracked the code for all life molecules, even our very own DNA. This is a huge update because just a couple of years back, AlphaFold was all about figuring out protein structures. I know you're eagerly waiting to learn about the original release and how the model works, so without any further ado, let's unfold how Google's DeepMind AlphaFold 3 is about to change science forever. So the big official news is that the new AlphaFold 3 model is 50% more accurate than its predecessors. And secondly, the technology, which was only limited to protein structuring, can now help figure out the structures of DNA, RNA, ions, modified residues, and even ligands. CEO Demis Hassabis told reporters that AlphaFold 3 is a major leap in AI's quest to unravel biology's mysteries, and it builds upon the breakthrough of AlphaFold 2. The model comes with a massive library of molecular structures. In this case, it's not about hundreds or thousands, but we are talking about millions of structures. Wondering how the models will work? Researchers input a list of molecules, and AlphaFold 3 uses a diffusion method to create a 3D model of the new combination. Yes, the diffusion method here is quite similar to what we see in text-to-image models like Stable Diffusion, but there are some differences which we'll discuss later in the video. AlphaFold 3 at the moment is revolutionizing Isomorphic Labs' understanding of new disease targets. DeepMind isn't keeping this tech to themselves. They're offering the AlphaFold server for free to researchers, letting them predict biomolecular behavior without worrying about computing power. This server is available for academic and non-commercial use, while Isomorphic Labs partners with pharmaceutical companies to use AlphaFold in drug discovery. Google says that they are working with scientific organizations, academia, and policymakers to ensure AlphaFold 3 is used effectively. Their academic paper notes some biosecurity experts' concerns that AI models might help create dangerous pathogens and toxins. However, Google has taken full responsibility for the release, claiming they only went public after assessing potential hazards and consulting with microbiologists, biosecurity experts, researchers, and industry specialists. With this new model, we can expect fields like medicine, agriculture, material science, and drug development to benefit by speeding up the testing of potential discoveries. But how does this model actually work? Guys, things are about to get a little technical, so bear with me, because I will simplify what these technical details mean. AlphaFold 3 builds on the setup of AlphaFold 2, but includes significant enhancements to handle a wider variety of chemical entities with less customization. Firstly, the multiple sequence alignment processing has been streamlined. The new MSA embedding block is simpler, and it uses a pair-weighted averaging, which reduces the number of blocks compared to AlphaFold 2's evoformer. The pair former, used in AlphaFold 3 instead of evoformer, focuses solely on pair and single representations, maintaining largely unchained pair processing and block numbers. The talk of the town, however, remains the new diffusion module, which replaces AlphaFold's 2 structure module. The diffusion module operates directly on raw atomic coordinates and a coarse token representation, eliminating the need for rotational frames or equivariant processing. It predicts true coordinates from noised atomic coordinates, enabling the network to learn protein structures across different scales. During interference, random noise is denoised to generate a final structure, thus maintaining prediction accuracy while reducing complexity. Generative training helps avoid the need for torsion-based parametrizations and violation losses, allowing AlphaFold 3 to handle general ligands without regarding global rotational and translational invariance or equivariance. To address the risk of hallucination, where the model might create plausible but incorrect structures, a cross-distillation method is employed. This method enriches the training data with predicted structures from AlphaFold Multiple version 2, helping AlphaFold 3 better handle unstructured regions. By learning from the successes and failures of its predecessor, AlphaFold 3 significantly reduces hallucination behavior and improves its ability to generate reliable and biologically meaningful structures. Now that was a lot of geeky stuff, but what exactly does it mean? Let me explain how these changes make AlphaFold 3 superior to its predecessors. So the first major change is the introduction of a new diffusion-based architecture, which replaces the AlphaFold 2 evoformer with the streamlined pairformer module. This change boosts the system's ability to handle multiple sequence alignments and focuses on predicting raw atomic coordinates rather than rotational frames. As a result, AlphaFold 3 can accurately predict complexes for almost all molecular types in the protein data bank, which remains the best resource for 3D structural data used in training and evaluating models like the AlphaFold. AlphaFold 3 also excels in predicting different kinds of interactions, such as protein nucleic acid and antibody antigen, with better accuracy than specialized tools in previous versions like AlphaFold Multimer V2. The new diffusion model improves the system's ability to clean up atomic coordinates, improving its understanding of protein structures on different scales. This generative capability allows for a more detailed exploration of molecular structures, improving predictions of both local and global configurations. Most importantly, AlphaFold 3 addresses previous issues with stereochemistry and bonding patterns, as this model can handle different types of biomolecular interactions. The shift to a diffusion-based module also simplifies training and inference processes, leading to faster and more efficient model development and deployment. AlphaFold 3 has truly made groundbreaking breakthroughs, but this model alone cannot revolutionize the fields of medicine and drug discovery. I know this might sound a little harsh, but there are reasons backing these claims. Look, AlphaFold 3 excels at predicting molecular structures, but drug discovery demands more than just structural insights. Understanding functional implications within biological pathways requires computational and experimental efforts on a different scale altogether. Key factors like pharmacodynamics and pharmacokinetics, how drugs interact with targets and how the body processes them, are meant to be considered for efficacy and safety. And in all these areas, AlphaFold 3 falls short. AlphaFold 3 struggles with predicting protein dynamics and conformational changes over time, which are vital for understanding drug binding. It particularly has trouble with regions lacking fixed structures, and such regions commonly appear in drug binding sites. It also can't predict the effects of post-translational modifications like phosphorylation, which are crucial for regulating drug targets. Not only that, it's limited to predicting structures of individual proteins or small complexes, whereas many drug targets are large multi-protein assemblies. AlphaFold 3 also cannot forecast the effects of mutations on protein stability, which is important for personalized medicine, and it doesn't model the complexity of the cellular environment, including molecular interactions and crowding, which determine drug efficacy. Drug discovery also involves predicting toxicity and side effects, which requires rigorous experimental validations. And again, AlphaFold 3 falls short here as well. These limitations of the best biological structure modeling toolkit we have today signifies that AI still needs more time to impactfully revolutionize drug discovery in medicine. Do let me know in the comments section below what you think about the future of medical sciences thanks to AlphaFold 3's breakthroughs. Some of the best videos I made are popping up on your screens. Click now, and I'll catch you there in a second. See ya!